The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on! The skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm your host, Desiree Shell. This week we're looking to the stars as we discuss the search for planets and intelligent life orbiting alien suns. We'll talk about the hunt for exoplanets with Ray Jayawardhana, author of Strange New Worlds, The Search for Alien Planets and Life Beyond Our Solar System. But first we're joined by Seth Shostak, senior astronomer with the SETI Institute. Enjoy! I'm talking to Seth Shostak, senior astronomer with the SETI Institute. Seth is the author of a number of books about the possibility of life on other planets, and he's also the host of SETI's weekly science radio show, Are We Alone? Welcome to Skeptically Speaking, sir.
It's a pleasure to be here, Desiree.
So let's start with some background. Explain what SETI is for us.
Well, SETI, of course, is just an acronym, Search for Extraterrestrial Intelligence, SETI. Almost my name, as it turns out, but that's coincidence. It's merely an attempt, it's actually profoundly an attempt to find not only life in space, but intelligent life. And the way we generally do that is to use very large antennas and hope to eavesdrop on radio signals, television signals, radar signals that might be coming off some planet far away, but the home to beings that are at least as clever as we are.
So you're not just waiting for alien spaceships to appear in the sky, you're actively searching for life on other planets.
We are, and as I say, intelligent life. And intelligence in this case means they're at least smart enough to build a radio transmitter. If they can't do that, if they're only as clever as, your average, dolphin or chimp, they may garner some respect amongst the other dolphins and the other chimps, but we're never going to hear those guys because, of course, they're not building radio transmitters. So, indeed, that's what we're trying to do. And I'm not, in fact, waiting for the spacecraft to appear in our skies, buzz the countryside, and occasionally haul people out of their homes, because I don't think that they're going to do that. But that's another story, perhaps.
So how did you personally get involved in SETI?
Well, to some extent, it's a matter of luck and accident in that I moved to this part of California. I'm speaking to you from the Silicon Valley, which is about 30 or 40 miles south of San Francisco. I moved here for reasons that had nothing to do with SETI or, for that matter, even my career. I moved here because I have a brother in this area, and he had a software startup company he wanted me to help him with. So I did that more than 20 years ago. But it turns out, rather coincidentally, that this is also the home of the SETI Institute. That's because NASA has a big research center here as well. So the startup company that I was working with my brother, unfortunately went ventral side up after about 18 months. So I was without a job, and at about that time, the SETI Institute called me up and they said, "Would you like a job here?" Now, I have to say that my background has been in astronomy. I have some degrees in physics and astronomy, and in particular radio astronomy. So I knew the technology of SETI. I knew how that worked. And beyond that, I've always been interested in aliens. I don't think that's particularly special. I think a lot of people are interested in aliens, but it has been an interest of mine for quite some time.
So how exactly are you looking for aliens then?
Well, the strategies we use depend on the experiment. We run various experiments, but a very straightforward one would be to, for example, pick out stars that are relatively close to us. When I say relatively close to us, that means within a few hundred light years. Now, most listeners will know what a light year is, but it's just the distance that light travels in 1 year. It's about 6 trillion miles or 10 trillion kilometers. So that's quite a piece. The nearest star to us is 4 light years away, other than the sun, of course. But the stars that we might find in a list that we could make up might be, 50 light years away, 100 light years away, 200 light years away. And we point the antennas in the directions of these stars in the hope that at least some of them might have planets with life, even intelligent life. And we use specialized receivers and a whole bunch of clever software trying to find a signal that's coming from those directions that is made by a transmitter. We don't really care what they're saying, not in the first instance in any case, but we are looking for signals that only transmitters could make.
So what kind of signals? Are they ambient signals, like TV and radio broadcasts, or are you looking for deliberate attempts to send signals?
In a sense, we don't care whether the signals that we pick up were deliberately sent our way for who knows what reason. Perhaps the aliens have some interest in increasing sales of some product. Perhaps they want us to buy their used cars. I mean, who knows? That would be a deliberate broadcast. And, of course, a deliberate broadcast, if it were aimed our way, might be very much easier to find because, of course, if it is aimed our way, it'll be stronger. On the other hand, I don't imagine the aliens are doing that because I doubt that they know we're here yet. Our own signals have not gone into space very far yet, so they probably don't know about Homo sapiens. But we don't care. Maybe we could pick up a signal that really wasn't intended for us. It's just the local weather report for this part of the galaxy. We just picked that up. It doesn't matter.
Well, there's an awful lot of sky out there, so how do you choose where to aim your antenna?
Well, that's true, and that's probably the reason we haven't found a signal yet. We've just really kind of scratched the surface. We haven't investigated a whole lot of celestial real estate yet. But you try and, take your best shot at any given stage in the knowledge you have of what's out there. I mean, 10, 20 years ago, we didn't know about any planets beyond the ones that circle the sun. But we assumed that they might be common. We didn't know that. It was just an assumption. And we pointed the antennas in the directions of stars that were very much like our own sun in terms of how bright they were. Because we figured, look, we don't know whether other kinds of stars could also have inhabited worlds around them, but we do know that stars like the sun could because we are one. We are one. So we would just point at sun-like stars. And we've looked at maybe 750 or 800 of those so far. That's not a very large number. Today, we know from work that's taken place in the last 15 years, and most recently, thanks to NASA's Kepler mission, that probably most stars have planets, or at least half of them do, and that's pretty close to all of them if you're an astronomer. Very little difference between half and all. And not only that, we're finding that some of these planets look like the kinds that might have liquid oceans and atmosphere. So when you learn that kind of thing, when you finally have the astronomical knowledge to say, hey, look, around that star over there, there's a planet that's just at the right temperature to have maybe liquid water on the surface, of course, you will point your antennas in that direction first.
So what would you accept as a hit, let's say? What kind of information would you have to see in a signal?
Well, we get signals all the time. If you point a big antenna at the sky and you have a receiver, as we do, that can receive, many tens of millions of channels simultaneously, right? You don't have to turn a knob. You get them all at once. You pick up signals, every few seconds you pick up signals. You pick up signals all the time. You have to sort through those. Now, is the signal, do you see the signal no matter where you point the antenna? If you move the antenna around a little bit, do you still see the signal? In that case, it's just a big transmitter here on the Earth. You can throw that one away. Is the signal at 1527.0000 megahertz on the dial? Well, that 0.0000, that bespeaks an earthly engineer. That wasn't an alien. They don't have the same definition of cycles per second that we do because they have a different second. So, there are all these very simple tests. In the end, you look for a signal that's coming from a spot on the sky that's moving across the sky together with the stars. And, if you find that, then you would start calling people up at another observatory and say, well, you check it out. And if they find it too, then I suspect you could book your trip to Stockholm and collect your Nobel Prize.
But so far, you haven't received any confirmed transmissions.
We haven't found it yet. Otherwise, actually, you would know about it because in our experience, whenever we have a promising false alarm, and we've had a couple, not too many, but we've had a few, the media, of course, immediately get wind of it and they start calling us up. So if we had even a candidate that was looking good, you would already know about it.
You're listening to Skeptically Speaking, and I'm talking to SETI senior astronomer Seth Shostak. So how much data does SETI produce in an average day then?
Well, some SETI programs do indeed just record data all day long, then they ship that data off to wherever their home offices are, usually at a university, and they play back the tapes and then they analyze the data at leisure. We don't do that. We analyze all the data in real time. In other words, as the data are coming in to the antennas, we're analyzing it. Now, how much data is coming in? Well, let me think about that. It's on the order of maybe, 100 megabytes per second. It's on that order. It's somewhere a couple of hundred megabytes per second. It's an enormous data stream, of course. That's a lot of bit pleasure. And in fact, we can't afford to record it and look at it later. So we look at it right away. We have some electronics, some computers fundamentally, that paw through all those data and decide, look, is there a signal here? And if there is, it orders the antennas to check it out right away rather than finding it, 3 days later and deciding, gee, maybe we ought to go back there and to that position on the sky and look again. So the advantage of doing it in real time is that you can check it out immediately. The disadvantage, of course, is that you don't you throw the data away almost as fast as you get it.
Well, you have a pretty popular crowdsourcing system as well, don't you?
I think you're probably referring to SETI at Home.
That's the one.
That's actually not our project. That's a project of the University of California at Berkeley, their SETI program. And because of the way they take their data, they can't check out signals right away because the telescope they're using is not under their control. So it's moving across the sky in sort of random ways. So it's okay for them to just process the data later. So they do indeed record their data, and then a certain fraction of those data are distributed on the internet for the SETI at Home screensaver. More than 7 million people have downloaded that screensaver. I don't actually know the current tally of people that have used that program, but it's an enormous number. Very, very successful way to process a lot of data.
So let's say one of those at-home users found a signal, and it looks like it needs to be examined more closely. Do you tell them about it?
Well, the Berkeley guys presumably will tell them about it if that signal is found not only a second time in the same place in the sky and at the same frequency. In other words, at the same spot on the radio dial. To find it once would not get anybody terribly excited because, just noise in the receiver and so forth will produce spikes that look like a signal every now and again. If you find it twice, it turns out that even finding it twice is still likely to occur just as the result of chance. But if you find it 3 times, if 3 different people find that signal, then indeed what the Berkeley astronomers would do is go back to another telescope, actually get control of the telescope and look specifically in that direction and see if they find it again. And if they do, then presumably all those people that had found it with the screensaver would get an invite to come to Stockholm too, or at least a nice postcard.
That's quite the selling point right there. You're listening to Skeptically Speaking. We'll be right back with more on the search for extraterrestrial intelligence.
Skeptically Speaking wants you to question everything. To be a part of the discussion, call and record your question on our listener question line at Speak 73101. That's 773-257-3101. Long-distance charges may apply. Sunday nights at 6 Mountain Time, join our Ustream chat room to listen and ask questions as we record interviews live. Just click the Listen Online button at skepticallyspeaking.com. You can also email your questions and comments to live@skepticallyspeaking.com, or if you're on Twitter, tweet us at Skeptical Radio. And now back to the show.
Welcome back to Skeptically Speaking. I'm Desiree Schell, and I'm talking to Seth Shostak, senior astronomer with the SETI Institute. So earlier we were discussing the criteria that SETI uses when it's looking for signals. So it sounds like in order to get a confirmed hit, you'd have to be looking in the right part of the sky where a technological civilization was active, and it would have to have gotten to us at this point in history, correct?
That's right. A lot of things have to go right. It's been sometimes likened to, firing a bullet that, by sheer good luck, happens to intersect another bullet fired by somebody else with a gun a couple hundred yards away.
What are the odds of finding a signal with that many variables?
The difficulties of this search are such that I'm not surprised that we haven't found anything so far. In fact, I would be quite surprised if we had found something so far, because we haven't looked at enough star systems over a wide enough range of frequencies with enough sensitivity. That's my opinion. But over the course of the next, say, 20 to 25 years, the equipment gets faster. And it gets faster mainly because we're improving our computers. There's something in the Silicon Valley known as Moore's Law. A lot of people know about it. Moore's Law, and the name just comes from one of the co-founders of the Intel Corporation. It only says that, every 18 months, the amount of compute power you can buy per dollar doubles.
Right.
That's just the improvement in technology. And it's really an economic law because the computer manufacturers, of course, want you to buy new equipment. Now, that also, it turns out, applies to SETI. We more or less double the speed of our searches every 18 months because a lot of the speed depends on this digital processing technology. So if you start from there and just assume that this is going to continue for a while, then you can say, all right, we've only checked out 750 or 800 star systems as of today. But in the course of the next 24 years, we'll check out about 1 million star systems. And I think if you check out 1 million star systems, it's, a supposition. But my feeling is that's the right number and that we have a good chance of finding something. So I hope that we can keep doing the project for the next 24 years, because I don't think that this is a hopeless project. I don't think it's a project that will take thousands of years. I think that if it's going to work, it's going to work within a few decades.
Well, speaking of that, SETI recently had to suspend its operations because its funding was pulled. Can you explain what happened?
Yeah. What happened is that our telescope, which is the Allen Telescope Array, this is the thing we've built together with the University of California at Berkeley, with their radio astronomy group, not their SETI group, the radio astronomy group. The SETI Institute, that is, we found the monies, largely from Paul Allen, but also many other donors, to actually develop the technology and build the instrument, at least as much of it as we have now. We have 42 antennas up there in the Cascades of Northern California. The design goal is to come to about 350 antennas, not 42, but that takes more money. But in any case, we put up the money to build it, and Berkeley was putting up the money to run the observatory, to actually, have the staff on site to maintain the equipment, to run the equipment, to take the observations, and so forth. Well, their funding has run into difficulties. To some extent, that's because of the grants from the National Science Foundation here in the United States have been reduced. Beyond that, the state of California, as several states in this country, is broke, right, to put too fine a point on it. And that affects the UC Berkeley funding as well. So the university has less money to put into the observatory. So they just simply don't have the money to run the telescope, and we don't have it either. And so we've had to put the telescope into what's called hibernation. In other words, it's sitting there, and there's a skeleton staff that maintains it, but it's not taking data because we don't have the money to pay people for that or the cost of the equipment. So until we can find that money, it's in hibernation, and I hope that it won't be in hibernation too long and we'll get it back on the air, but that depends on money.
I've seen a few infographics comparing your annual budget to other government expenditures. Do you have a favorite comparison by any chance?
Well, I've seen some of these graphics myself. Yeah, if you compare it to the cost of a lot of weapons systems, and that seems to be the thing that most people love to compare this to. I'm not quite sure because SETI isn't really a weapons system, but in any case, it's very cheap compared to an Air Force jet or an Army helicopter or anything like that. On the other hand, you could say that about a lot of things. So, that's unfortunately maybe impressive around the dinner table, but the problem is that there's really no government funding for SETI per se in this country. It's been privately funded for the last 18 years. And it's rather difficult to raise even the modest amounts of money that are required to run the telescope. And we're talking about a couple of $1 million a year. Now, that's, you could say, well, that's nothing for somebody like, Bill Gates, right? Well, it's true, it's nothing. But that doesn't mean just because it's nothing compared to his total net worth that's where he's going to spend his money.
Right.
So, these graphics that show, we spend more on, cat food every 10 hours than you do on SETI or whatever. I mean, that may be true, but people aren't going to say, I'm not going to give my cat his cat food. It does put numbers in perspective, but doesn't raise the monies.
Well, how long do you anticipate SETI being out of commission then?
Well, I don't know. I am always kind of an optimistic sort of guy. I'm always sanguine about these things, and I think that within a few months we may have found a way to reopen the telescope. But that's me talking, right. And I certainly hope I'm right about this, but I usually hope I'm right about anything I say. And experience has taught me that that's not really true.
Right. Well, are there other facilities in other countries that are listening while SETI is down?
Yes. We're not the only people doing SETI, it's true. The University of California at Berkeley, which we've mentioned earlier, certainly does a wide range of very interesting SETI experiments, in fact. And they use other people's antennas to do that. There's also what's called an optical SETI experiment. In other words, one that uses a different kind of telescope, one that most people would recognize. It has mirrors and lenses to look for flashing laser pulses coming from other star systems, and that's being run at Harvard University in Boston, Massachusetts. There are some experiments overseas, not too many. There's one in Italy at the University of Bologna, and there are some experiments in Asia, in particular. South Korea is interested. Japan has been interested. They haven't done too much. The Chinese say they're interested. So, it's a very limited endeavor worldwide, and for the past 15, 20 years, it's been mostly an endeavor here in the United States. And I'm not quite sure why that is. There's something cultural in that, because other countries, including Canada, by the way, have the technology, they have the expertise, and frankly, they have the money to do this, and yet they're not. So that's got to be culture.
So maybe walk me through what would happen if, let's say, I'm not even going to say if, when you find a signal that there's evidence of alien life, what's the process?
Well, there actually is sort of a worked out procedure, although it never seems to, we never seem to follow the procedure whenever we get a signal that looks promising. I mean, as I say, we find signals all the time. And the computers that are running the antennas, because, all of this data collection and analysis is done automatically by software. You don't sit there with a pair of earphones on. I mean, there's no way you can do that. So it's all pretty automatic. But if the software finds a signal that looks like it is passing all the tests, that it is a real candidate for being an extraterrestrial signal of the sort we're looking for, then eventually it begins to vie for your attention. It tries to wake you up and say, hey, look, you might want to check this out further. And you would spend a couple of days just looking at the signal, making sure that it passes all the tests that separate ET signal from, signal being generated by telecommunication satellites orbiting the Earth, for example. And then eventually you would call somebody up at another observatory and ask them to look too, because you probably wouldn't believe it until somebody else could find it as well. But in all this time, and this might be, half a week or a week, in all this time, you can be sure that the media will be calling you up, because there's no secrecy in this endeavor. Right. And consequently, everybody's sending emails to their girlfriends and boyfriends saying, hey, interesting signal here, and they're putting it on their blog and who knows what else. It's our experience that whenever we have a signal that looks promising, that the newspapers and the TV people are calling up within hours. So that's what would happen. There would be this big story even before we had confirmed the signal. So I expect there will be false alarms in the future.
So do you think that the media is actually an obstacle in this at all, or you're okay with the way that they treat this?
Well, I don't have any problem with the media myself. Personally, I think that the media, the media is just an in-between between you and, the populace, right? So it's kind of hard, it seems to me, to say I don't like the media when really what that says is, well, I don't like the general population. I mean, it probably will lead to situations that are unfortunate in the sense that everybody will get all excited, and then it turns out, oh, well, it was just we were just fooled by a bug in the software, or it was a telecommunications satellite. We've had that sort of experience, actually. And so, that's too bad, because it kind of makes people think, well, these SETI guys, they don't know what they're doing. So, that's the downside of it. But on the other hand, I think that it's very important that the public know that there would be no secrecy here, because a lot of people are conspiracy-minded.
And that's where I was going with it. When there is a bug, is that where conspiracies are born?
Well, I think conspiracy theories in this field largely derive from the fact that a lot of people believe that the aliens are here already, buzzing Earth, right? And 1/3 of the population believes that. I don't, but 1/3 of the population does. And when you say, well, why is it that if that's true, I can't go to my local science museum and find out all about it? Right. And the answer to that is that, of course, the government, whichever government you're talking about, has managed to keep all the good evidence from you. They've squirreled it away somewhere. Now, even aside from whether the governments are motivated or even have the capability of doing that, that requires secrecy, right? And so people assume that, well, SETI would be squelched by the government too, because the government clearly doesn't want us to know about the aliens. So if we found a signal, the assumption of many people is that the government would immediately come in and shut everything down. When we've had false alarms, I have to say, no arm of the government, local, state, or national, or for that matter, the UN, has shown the slightest bit of interest in either shutting us down or giving us money to do the experiment.
So what can we do for SETI, us regular people?
Well, obviously, I mean, if you can get involved, if you can make a contribution to, opening the telescope and so forth, that's a very direct help. The SETI Institute has a membership organization called Team SETI, so people could, in fact, go to the website, which is just SETI.org, and sign up there. There's also a participatory data analysis program that the Institute runs called SETI Quest. So people who are interested in looking at data and deciding, is there anything interesting in it, could do that. So those are the sorts of things. I mean, it's just a matter of nosing around the Internet for maybe 3 minutes, and you'll find all sorts of things that you could do. I think the most important thing from my point of view is that people know about this experiment, and I think if they know about it, they'll recognize that while the chances of success are uncertain, it's such an interesting question that I think it's really worth a little bit of effort.
And so if anybody has any millionaire friends, they should really, really encourage them to give money to SETI then.
Well, yes, I would be disingenuous if I said that was a bad idea.
Thanks very much for being here, sir.
It's been my pleasure, Desiree.
We've linked to Seth Shostak and his work at SETI on our website at skepticallyspeaking.com. Stay tuned for Ray Jayawardhana, the author of Strange New Worlds, The Search for Alien Planets and Life Beyond Our Solar System, after these messages.
Skeptically Speaking is rebroadcast on a number of fine radio stations. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
My guest today is Ray Jayawardhana, the professor and Canada Research Chair in Observational Astrophysics at the University of Toronto. Born and raised in Sri Lanka, he holds a bachelor's degree from Yale and a PhD from Harvard. He's the author of Strange New Worlds, The Search for Alien Planets and Life Beyond Our Solar System. Welcome to the show, Ray.
Pleasure to be here, Desiree.
So since no one was there for it, how exactly have we pieced together the history of our own solar system?
Oh, we've got clues from many different avenues that have helped us piece together our own solar system's history. In fact, just to make a personal connection, I was in Antarctica over December and January as part of a team collecting meteorites. And these meteorites obviously are leftover debris from the early days of our solar system. So that's one of the physical clues that we have, for example, for determining the age of the solar system. But then we also learn a lot about our own solar system by looking at other solar systems at different stages of formation and evolution. In particular, looking at baby solar systems, ones that are just forming out of disks of dust and gas around young stars, and tracking them and studying many different examples to understand what early solar system might have looked like. And then a third piece of evidence would be related to theoretical work, including computer simulations of how planets might assemble out of dust and gas.
Can you explain the idea of stellar nurseries? I find that really interesting.
Well, stellar nursery is basically a region of space that's a cloud of gas and dust out of which new stars are born. So one of the best-known examples in our relative local neighborhood, cosmically speaking, is in the Orion Nebula. If you know the constellation Orion in the night sky, and you look just below the three stars that make up the Orion's belt, roughly sort of in the middle of the sword of Orion, is a little fuzzy patch, and that's one of the big clouds of gas and dust nearby that is a stellar nursery, where literally thousands of new stars have been born in the last couple of million years.
Well, how is a star born?
The evidence that we have to date is strongly suggesting that stars basically form out of the denser bits of these big interstellar gas clouds, and they probably contract perhaps by some external disturbance that sets them going, but in the end they contract under their own gravity, and they shrink in size, get denser, and any spin that the cloud would have because of conservation of angular momentum would basically spin it up. So basically you end up with a rapidly spinning ball of gas, which when it gets hot enough and dense enough in the core, if the object is massive, sufficiently massive, then you get nuclear reactions. And that's when we say a star is born, when the nuclear burning begins at its core.
How do we know that?
It comes together from a variety of pieces of evidence. So one is what we know about our own sun. For example, this is sort of to give a kind of an example from a very different bit of astronomy. One of the strongest pieces of evidence we have for nuclear reactions going on in the core of the sun is through the detection of all these ghostly particles known as neutrinos, where every second of every day, trillions and trillions of these particles are going through your body. But they interact with other matter so weakly that physicists usually have to have Olympic-sized pools of cleaning fluid deep underground to collect a few. But just measuring the numbers of these neutrinos tell us the rates of nuclear reactions in the sun. So that's for a grown-up middle-aged star. Now, in the case of young stars, we can actually look, especially in the infrared, through a lot of the dust clouds that would otherwise obscure these newborn stars. By looking in the infrared, by looking into the microwave part of the spectrum, into the longer wavelengths, then we can actually penetrate through the dust and see new stars coalescing. We can see them lit up. We can see material forming these beautiful disks of gas and dust around them. So we really can see with our telescopes on the ground and space different snapshots of this process, and that's how we piece together the full story.
That's what I wanted, sir. Thank you. So how about planets? How are they formed?
It seems the material for making planets is there along with the newborn stars. So the vast majority of these newborn stars, when we survey them at barely 1 million years old, seem to be surrounded by such disks of material. And that's the stuff out of which we believe planets form. And as I said, we could observe directly some parts of that process, some snapshots of that process. We can see how common those disks are. We can measure roughly how big they are. Then they tend to be perhaps a few times bigger than the size of our own solar system. We can figure out how much material there is, what their masses are, and they seem to have plenty of mass to make planets, a planetary system like our own. Some are a little bit more massive, some are a little bit less massive, so there's a range. We can measure their temperatures, so we can learn quite a bit about the physical nature of these objects. Now, the hard part is, of course, we can't directly see the dust particles actually sticking together, in a disk right. That's, hundreds of light years away, and that we can't necessarily, see at that resolution or see through, everything else around it. So that's where we need clues from other things like computer simulations. You basically write computer code that follow laws of physics as we know them. And try out various scenarios and see which ones actually lead to growth of what we call planetesimals, or little bits that would, eventually go into making planets. But there's also laboratory experiments that people do. In fact, even some experiments have been done on the space shuttle, for example, where in microgravity or in near zero gravity, trying to understand how little particles might stick together to make bigger pieces. So there's a whole range of clues one needs, and the process may be complicated, and we need different pieces of evidence from different processes, from observations, from modeling in computers to actual lab experiments to put it all together.
Approximately how long does it take to make a planet?
So this is one of the things I've actually worked on myself from one particular angle, which is through observations of these disks to try to figure out their lifetimes. So you can study stars of, 1 million years, 2 million years, 5 million years, 10 million years, and see at what point do the disks go away, or at least where you don't see the dust in small particles anymore. And that puts some limit on, how long it could take planets would have to build up, right? So that's one of the things I've worked on. I mean, it's a big question, so many different people have worked on it from many different angles. But the numbers we're getting are that most big planets like Jupiter, which are big balls of gas essentially, would have been fully formed within a few million years. Because after about 5 million years, we don't see much gas hanging around these newborn stars. So they must have been incorporated. If planets were going to form, they had to form by then, because you wouldn't have any gas left after that. Planets like the Earth, rocky planets, small planets, could take a bit longer, in fact, to reach their final form. It could take maybe a few tens of millions of years even. In the case of our own Earth, there's growing evidence, though perhaps it's not a slam dunk, but there's strong evidence that our own moon actually formed from the collision of a mass-sized protoplanet with the proto-Earth, and sort of by throwing out a bunch of material into orbit around the Earth, which later coalesced into the moon. So that might have happened some 50 million years after the solar system started to form. So it could have taken tens of millions of years, in other words, for the planetary systems to fully sort of get in shape.
You're listening to Skeptically Speaking. I'm talking to Ray Jayawardhana, Canada Research Chair in Observational Astrophysics at the University of Toronto. So there are people like you who are actively looking for planets. Why exactly?
The main motivation, of course, is to figure out our own place in the universe, to know how our own planet and our own planetary system stack up in a cosmic sense, in the cosmic context. So, it's an age-old question that we wanted to know whether we are alone in this universe. From everything we know in terms of numbers, there's, a couple of 100 billion suns in our galaxy alone. And then there are, up to maybe 80 billion galaxies that we know of in our universe. So the numbers are just truly staggering. It's hard to imagine that we would be alone. But that's one thing to speculate. It's one thing to argue, but it's a whole another thing to actually have evidence. So for hundreds of years, people have talked about there must be planets orbiting other suns. If the stars we see in the night sky are other suns like ours, why wouldn't they have planets? But we've gone a long way from that to actually having evidence of worlds orbiting hundreds of suns by now in the last 15 years. And I think that's a fundamental change from speculation to the realm of hard evidence.
Well, I just want to point out, the answer to that question would have been perfectly acceptable if you would have just said, because it's awesome. And that is...
it truly
absolutely.
is.
So how many planets have we found then?
In the 15 years since 1995, using telescopes on the ground, astronomers have confirmed some 520 planets orbiting other stars. And that's through several different methods. And then more recently, since NASA's Kepler Space Observatory was launched, just from the first year of data that was released back in February, astronomers have identified another 1,200 or so planet candidates. Now, we're being a little bit careful about these Kepler planet candidates because they haven't truly been confirmed yet, and they need to be followed up a bit more to really be sure that each one of them is really a planet and you're not being fooled by something else. But the point is that we're truly in an age of incredible discovery, where the pace of discovery is truly astounding to me. Just last year in 2010, and this was before the Kepler discoveries, just from the ground, astronomers identified over 100 planets in one single year. So it's really, we're really in the thick of it, and Kepler has come and opened the floodgates. So soon we'll be talking about thousands of planets and planetary systems. So it's not even a single planet around each star, but it's actually multiple planets in many cases. And I can give you a couple of examples if you like.
Mm-hmm, please.
Okay, so one would be, a planetary system that Kepler discovered, where what this telescope is doing is it's orbiting. It was launched from Cape Canaveral in March of 2009, and it's basically in orbit around the sun, and it's staring at one little patch of the sky continuously. And it's monitoring the brightness of about 150,000 stars to see if any of them have periodic dips in brightness. In other words, it's looking for planets that might pass in front of those stars. So for a brief period, for a few hours, for example, a star may get dimmer by 1% or a tiny fraction of 1%, and then come back up to its normal brightness, and then you'll see it repeated in a very periodic way. That could very well be evidence of a planet orbiting that star. And how long it takes to repeat will tell you what the period of the planet is. How big the dip is will tell you how big the planet is or small the planet is. Get a good idea of the size of the planet if you know the size of the star. So this way, in one case, Kepler found 6 different planets orbiting one single star. So it's a 6-planet system. And these planets are a little bit big, but compared to the Earth, they're roughly the size of Neptune. And 5 of those 6 actually have orbits that would fit inside the orbit of Mercury around our sun. So imagine that. 5 planets, in orbits that fit inside Mercury's orbit. So incredibly densely packed, rich planetary system. So the big emerging story, of course, we're all interested in twin Earths and prospects for life,
right.
But also the other big storyline emerging is the incredible diversity of worlds and architectures of planetary systems that are out there.
Well, let's go back one step, because the Kepler mission now, that's a search for exoplanets specifically. Let's define what exoplanet is for people.
It's a short form for extrasolar planet. Is another term that's used. So it just means a planet that's orbiting a star other than our own sun.
And what if an exoplanet resides in a habitable zone?
So what that means is that if a planet happens to be roughly, at the sort of distance from its star, that it would have the right sort of temperature to support liquid water on its surface. In other words, that it's not too hot and not too cold, that water wouldn't be frozen or in vapor form, but actually, a liquid on the surface. That's the kind of somewhat narrow definition we have at the moment for what a habitable planet might be. So the habitable zone is the distance from a star at which a planet would have liquid water on its surface, or could have liquid water on its surface. Now, it's the nature of science is that often our definitions turn out to be too narrow, or turn out to be, based on one example, which doesn't apply elsewhere. So I'm sure, our view of what sort of planet could harbor life will, almost certainly expand as we actually get closer to those discoveries. Because right now we're basing all of that. We have hundreds of planets and planetary systems to study now, but we still only have one planet for sure there is life we know of, and that's quite limiting in terms of looking for life elsewhere. We only have one example to base our search on.
We have a bunch of audience questions coming in. Let's do one from Steve.
How close would a new planet have to be before it would be feasible to send an unmanned probe to explore it, let alone a manned mission?
Planets are being discovered in our cosmic neighborhood, but we're still talking about light years or tens of light years. So given the technology we have today, the fastest spacecraft that we have, unmanned spacecraft we have launched so far, travel at a tiny fraction of 1% of the speed of light. So we're still talking about the kind of timescales that are way beyond a person's lifetime or even several generations. So I think if you really want to visit, we really do need to push for more advanced technology and achieve at least 1% or a few percent of the speed of light for unmanned spacecraft to be able to talk about this realistically. Now, that said, astronomers are looking for planets around some of the nearest stars. One of the stories I tell in my book, Strange New Worlds, is about the work that Professor Deborah Fisher at Yale now is doing, and she and her collaborators are trying very hard to find if the nearest star system to us, the Alpha Centauri system, for example, harbors a habitable world, because that would be, that's the nearest star we have. It would be really exciting if that one happens to have a planet of the right sort in the habitable zone. That might generate a lot of public interest and enthusiasm, and perhaps then, someday, if you're thinking about interstellar probes, that would be a great target.
You're listening to Skeptically Speaking. I'm talking to Ray Jayawardhana, the author of Strange New Worlds, The Search for Alien Planets and Life Beyond Our Solar System. And we'll be right back after this.
What is science-based medicine, and how does the media distort it? On the next episode of Skeptically Speaking, our guest is Dr. Stephen Novella, academic clinical neurologist at Yale University School of Medicine, executive editor of the website Science-Based Medicine, and a senior fellow and director of science-based medicine at the James Randi Educational Foundation. And we're joined by Atlanta Skeptics organizer Maria Walters to talk about the Grassroots Skepticism Workshop at Skepticon. That's next week on Skeptically Speaking on your local radio station or online at skepticallyspeaking.com.
Welcome back to Skeptically Speaking. I'm your host, Desiree Schell. I'm talking to Ray Jayawardhana. Jay is the Canada Research Chair in Observational Astrophysics at the University of Toronto and the author of Strange New Worlds, The Search for Alien Planets and Life Beyond Our Solar System. We have a question from Ken.
There's a lot of popular speculation that there might be a giant planet orbiting the Sun out in the Oort cloud. Could we use any of the methods used to hunt for exoplanets to try and detect a hidden planet in our own solar system?
Unfortunately, actually, the kind of methods that we use to detect planets around other stars are not the best way to look for such a world. Because, for example, we use a method called the wobble method or the Doppler method, where you watch the wobble of a star due to a planet tugging on it as it goes around. Now, if a planet around the Sun were that far away, it would take thousands of years for it to complete one orbit. So the kind of wobble that the Sun would have would take, to see one period, you'd have to wait thousands of years. So it's not the best sort of a way to search for such a world. A much better way is to try to actually detect it in an image, but it would be extremely faint. Plus, you have to identify it against the background stars that are much further away but might be at equal sort of brightness. So the best chance we have actually is through all sky surveys done in the infrared at infrared wavelengths, where you might take multiple observations over nights or weeks or months or years and see some objects moving. And this is the way that people discover often asteroids and comets. And maybe it's possible someday a much more distant, bigger body would turn up. And there are a number of exciting new facilities coming along that would allow for this kind of search. For example, all sky surveys that would survey the night sky completely every few days. So that would be a much better bet on how one might look for a very distant companion to the Sun.
You're listening to Skeptically Speaking, and I'm talking to Ray Jayawardhana, Canada Research Chair in Observational Astrophysics at the University of Toronto. So, Ray, what are the chances that we'll find a planet that's as warm and wet as Earth is?
I think the chances are quite good in the next couple of years, mainly thanks to the Kepler Space Observatory. This spacecraft, as I mentioned earlier, is monitoring some 150,000 stars, looking for planets down to about the size of the Earth. And in the next couple of years, we fully expect that it would be able to detect not just one, but likely dozens of planets that are not much bigger than the Earth, and that might happen to be at the right sort of distance from their stars to harbor liquid water on their surface. So I would say the chances of finding warm, wet, and probably rocky world is pretty high, and astronomers already have the capability to do so. Now it's just a matter of time to see some of these worlds orbiting their suns for multiple times. In other words, to see the planets transiting their stars several times to be sure and to rule out any false positives. Now, it's still a big jump from that to actually claiming whether there is life or not. It's one thing to say a planet is habitable for the kind of life we know of on Earth, but a whole another thing to claim it has life. So I think that second part will be still a challenging thing to nail down. And it's one we are very, very curious about, one we're very excited to know the answer to, and we're closer than we've ever been. But, unless we are very lucky, that may still be a challenging issue even a few years into the future.
And we have a question from Jeremy.
If we had found arsenic-eating bacteria, Would that have changed our definition of what we consider a habitable planet? What else could change the criteria?
In terms of life elsewhere, I agree that we certainly need to be as open as possible in looking for life that might at least appear different, even if in some basic underlying way the biochemistry may be similar, but chances are that the final product will be extremely different if life evolved originated and evolved completely independently elsewhere. It's hard to imagine why they would look the same. In other words. So we certainly need to keep our minds open, but at the same time, we're struggling a little bit, as I said, because we have only one example of a life-bearing planet so far. It's not very easy to generalize. So what most scientists are doing is coming up with techniques for looking for what we know, but then at the same time trying to keep an open mind and be on the lookout for anything that we don't know that stands out or that makes, some subset of planets, let's say, that Kepler discovers. If it finds thousands of planets and some, few dozen of them appear different for whatever reason, even if we don't know what that reason is, maybe those are the ones to focus on, and they may be the first hint of life on those planets. So it's sort of, looking for what we know and yet keeping our eyes open for what else might be there. That's sort of the strategy we have.
And we have a question from Tara in South Africa.
I'd like to know your thoughts on the Square Kilometre Array project, specifically whether South Africa would be a good site.
Ooh, loaded question. Just to kind of refresh what this is about, it's a proposed radio telescope, the biggest it would be if it's ever built, and South Africa and Australia, as I understand, are sort of leading contenders to host it. So it would be an incredibly powerful array of radio telescopes. It's one that would give us capabilities that are sort of hard to even fathom at the moment, and would certainly be quite exciting and interesting. I think both South Africa and Australia clearly have the geography for it. You want a relatively radio silent location, one that can operate freely for a long time. So, South Africa certainly is an excellent candidate for hosting it. I think in the end, it would probably depend a lot on the political will of who's willing to put up the resources and make the commitment to take the lead. There will be a process for making the final choice with the evidence at hand and with the kind of commitments that various countries are offering to bring it together. But it's a very exciting prospect, and certainly it seems like South Africa is actually, there's a lot of interest in astronomy in general in South Africa. I've been there a couple of times, and there's a lot of activity on the ground, and there seems to be a huge amount of interest in sort of promoting astronomy, both for the curiosity of it, the science, but also for the technological and societal benefits of sort of, as an inspiration for bringing more kids into science as a way of having a lot of technological spin-offs. And the Square Kilometre Array is certainly a very interesting prospect along those lines.
And a question from David.
Can you please speak about Juno, the Jupiter mission that will launch this summer?
It's one of several planetary missions that are underway that are very exciting. One that's going on right now is actually a space probe called Messenger, and that's at Mercury right now. The Juno mission is sort of the next step in our investigations of the giant planet, the biggest planet in our own solar system. So the idea is to build up on what's already known, and it's part of a NASA program called New Frontiers, and we're hoping that it'll give us a much better understanding, or we're expecting it will give a much better understanding of the internal structure of Jupiter, and that'll help us understand actually planets around other stars better as well.
And we have an email from Katrina.
Are you able to use standard techniques for looking at binary and multi-star systems to try and find planets, or can you only look at single stars?
Indeed, that's possible, and it is done. In the early days of exoplanet searches, often people using the wobble technique avoided binary stars, but since then astronomers have indeed looked for and found planets orbiting binary stars and multiple stars. This is quite important because a significant fraction of the stars in our galaxy are members of binary or triple or quadruple systems. So it's very important, if you want to know about how common planets are, to know whether these multiple star systems can also harbor planetary systems. And the answer seems to be that indeed they can, at least if the two stars in a binary system are separated well enough that planetary system around each one can be relatively undisturbed. Perhaps a more intriguing example would be if two stars can be extremely close to each other and you could have planets orbiting both of them. And I don't know such an example at the moment, but that would be very, very interesting. But also it's kind of, fascinating to think about, standing on a planet that orbits a star in a binary system, to have, not one sun rising and setting, but two or multiple suns rising and setting, so you may never have a real nighttime, depending on the configuration. So it's very exciting to think about a world with multiple suns.
And a question from Derek.
Do any exoplanet search teams use crowdsourcing resources the way that SETI at Home or Galaxy Zoo do?
I know there are a number of amateur astronomers involved in transit planet searches with backyard telescopes, and I think the Kepler mission is trying to get people involved at home with the public release of data to use some of these sort of crowdsourcing techniques to look for interesting phenomena that might otherwise be missed in their database. So there's interesting prospects coming up, especially with the vast amount of data that Kepler is bringing us.
And I will give the last question to Chris Lindsay.
If we found exoplanets that are in the habitable zone of other stars, would it be feasible to send interstellar probes with microbes in order to begin terraforming that world for eventual human life?
Well, it's the kind of thing that still, at the moment, at least in the realm of speculation, we're a long way from being able to send probes to, that cross vast interstellar distances. Perhaps a more interesting, or perhaps a more serious discussion to have is about, planets in our own solar system, for example, Mars. People have talked about, written about, and to some extent have sort of come up with schemes of how you might terraform a planet like Mars. But again, one has to be extremely careful because on the one hand, most scientists would probably want to make sure there isn't any life. Mars doesn't have a life of its own, because before we think about contaminating it with microbes from the Earth. So the first step would be to explore Mars to really find out if there is any evidence of current or past life, bacterial life on it, or maybe just underground or under the permafrost. So that's the kind of exploration. That's the first step, and then maybe in the long run, one can talk about that in planets in the solar system. Doing that for planets that are tens of light years away, that might take many tens of thousands of years to get to. It's still a bit down the road.
That's it for our time, and I think that's it for your voice. Thanks very much for being here.
Thank you, Desiree.
You can find links to Ray Jayawardhana and his work on our website at skepticallyspeaking.com. While you're there, we'd be very pleased if you'd click the links to Facebook, to Twitter, to iTunes, and anything else where you can listen to past episodes, subscribe to the show, or leave a review. Thanks very much for listening, and we'll see you next week on Skeptically Speaking.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell, gonna raise a little hell, break the spell of Pavlov's spells. Cause we're skeptically speaking, our mind reading tarot cards and witches, psychics, and their spoon-bending mind tricks. All the humbug, flim-flam, frauds and shams, the charlatan who I don't think you understand. It's the hocus pocus, out of focus locus, eroding the brain, making gains on the hopeless. Let the crystal ball fall, smash on the floor, leave the pieces alone. We don't need them anymore. Just a microscope, telescope, magnifier, reading in between the lines of these lies. Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Shell, gonna raise a little hell, metaphorically that is, cause we're skeptically speaking.
Skeptically Speaking is produced with the support of CJSR 88.5 FM in Edmonton, Alberta, Canada. Our studio assistants are Brent Kelly and Lisa Skovanek. Ryan Bromsgrove is our studio technician and research assistant. The show is produced and edited by K.O. Myers. Our theme song was written and recorded by A.O.K. And I'm your host, Desiree Schell.